Let's look at how to solve problems with derivative with inverse trig identities. So what do I mean by that? What is inverse and what is trig identities, right? So so because we already saw a few examples of trig identities, we can say, well, so uh, anything with trigonometry on it, like sine, cosine, tangent, is a trig identity. And what is the inverse? So that is what we're going to deal next. Let me share my screen and then I will begin writing on it. Cool. So just like the regular derivative of trigonometric identities, we also have formulas that we need to consider for inverse trigonometric identities. So let's quickly recap what's inverse. What is an inverse function? So if you recall from your pre-calculus or any other classes like algebra class, inverse function is nothing. It's only a definition of a function. Y equals f of x equals, it could be something, right? Some inverse. Well, in this case, we're dealing with trigonometry, so we should write something like tan inverse x or theta or sine inverse y, not y but x. So anytime you see power -1, you recognize this as an inverse trigonometric function. Okay, so with this brief introduction, let's go to the problem. So here we have a problem. It says y equals arctangent of 1 over x. So what is the dy dx of this function? So what is the dy dx of this function, or the first derivative of this function? Well, so let's see what we have in our formula sheet. It says, so this is the formula we're going to use. So from this table, even if you don't know all of them, it is highly recommended, or it's very useful to know at least 3 of the top formulas, because it's going to come up over and over again. So in this case, we will be using this property to solve this problem. So it says y equals arctangent of 1 over x. What is dy over dx? So let's begin one by one. Okay, so let's rewrite this as y equals tan inverse of 1 over x, correct? And we need to find dy over dx. Well, so that would be d over dx of, because y is given as arctangent of that, so I could write d over dx of tangent inverse of 1 over x. Okay, so let's recall formula. Recall, so tan inverse of x, the derivative of this is 1 over 1 plus x squared. You can also verify this over here. So writing arc tangent is same as writing tan to the power -1. So this is equivalent to writing tan inverse 1 over x. Okay, so just notice arc keyword in the front and the -1 on the top. Fine. So this is pretty straightforward. We could just go ahead and write this uh, as the formula. But here's a catch, because the formula gives us the relation for x, right? Just x, but not x to the power -1 or 2 or something like that. So we have to treat this as one variable. So for simplicity, I'm gonna put u equals 1 over x, right? So if I do that, so I can see the whole thing as d over dx tan inverse of u, right? So where u equals 1 over x. So that means this is only to visualize how to simplify a complicated looking problem. So, so because u equals 1 over x, so if I convert that to the formula over here, so our solution should look like 1 over 1 plus u squared, right? So that should be 1 over 1 plus. So if I put the value of u back. So it will be 1 over x squared. So if I simplify this further, it will be 1 over 1 plus 1 over x squared. And this is going to be equal to x squared plus 1 plus x squared. So how did I get this? Well, basically you take the common denominator. So it will be 1 over x squared plus 1 over x squared. And then you flip them. Okay, I hope you understand this. This is a very simple but very crucial problem to understand what we're gonna do next. Any questions so far? Okay, so let's go to next problem. It says y equals arctangent of sine x minus 1. So how do we do this problem? This is somehow similar to next like previous problem, but let's see what this problem is giving us. This it doesn't have any denominator sign like previous problem, but it is also somehow similar, right? So we could just translate this to what we just did before. So it could be y equals sine inverse of x minus 1, correct? So we need to find dy over dx equals, so just write d sine inverse x minus 1 over dx, correct? But one thing in a different derivative is to recognize what we are differentiating a function with, right? So if you notice here, this is the variable inside sine is x minus 1, but here the the denominator is dx. So that means we have to adjust something here, right? So that means, so recall um if you recall chain rule, so you could convert these to something like this: d of sine inverse of x minus 1 over d of x minus 1, right? Then what you're going to do is d of x minus 1 with respect to x. So essentially what I just did here is that I made the variable same, so we could just use like derivative rule, normal derivative rule, which is d over dx of x to the power n is n x to the power n minus 1, right? And here, if you cancel these two, they will be same, right? So we're just adding same thing on numerator and denominator to make it easier for us. Okay, so let's move ahead and solve it. So that would give us, so this part is, well, let's do the easier part first. So for this is going to be 1, right? So derivative of x with respect to x is 1, and derivative of -1 is just 0. So that the answer will be 1 for the second half. The first half is kind of new to us because it has -1 on its power. So that means it is an inverse function, right? So you have to recognize this as inverse trig function. Okay. All right. So what should we do next? So we know that this is the inverse trig function. So we should go to the formula sheet and look for the relation for that formula. So let's go back and see here, what is the derivative of arc sine x, right? So this is the relation we're going to use. So it will be 1 over square root of 1 minus x squared, right? So that means this is going to be 1 over the square root of 1 minus. So in the formula, there is 1 over square root of 1 minus x squared, right? But because we have x minus 1, what we're going to do is I'm going to do x minus 1 squared. Okay, so that's why I did u equals x minus 1 earlier so that you could see the change of variable. So over here, if you notice, this whole thing is u. I could consider this as u, right? And I can basically say, okay, so du over dx is basically 1 over square root of 1 minus u squared, which is the basic same thing. So we just made things easier for us. So let's simplify this further and write 1 over square root of 1 minus x squared. So we're going to expand this term right here. So 1 over x squared minus or plus 2x minus 1, right? So immediately we could cancel these two. And let me move these right here so I can have some space. So this can be written as 1 over square root of 2x minus x squared, right? So this is the first part, but the second part is 1. So basically the answer is going to be the same. So 1 over square root of 2x minus x squared. Okay, so I hope you are getting this. This is also one of the important way of doing inverse trig function, especially when we see when we have to adjust the variables to use the formula. Okay, any questions before I move to the next problem? Okay, so let's go to next problem. It says y equals 1 over a and arctangent of x minus a. Okay, finally we are here, something new, right? So we have y equals 1 over a. So we got one variable in the front, and we also see that this is an inverse function, and there is another variable which is in fraction. So this is also a very conceptual problem, okay, because it involves many other techniques that we use in derivative. So let's rewrite this first. Y equals 1 over a and tan inverse of x minus a, right? Because I said arc, you could say arc tangent equals tan inverse. All right, so then the next step is to find dy over dx, right? So I could write d over dx of 1 over a tan inverse x minus x over a, correct? All right, so we're doing derivative with respect to x, but here's a value 1 over a, which is basically a constant, right? So if you know the rule for derivative of a constant, you could just bring it in the front, right? 1 over a, then d over dx of whatever is left inside, which is tan inverse of x over a. Okay, cool. But another thing here is that we're doing derivative with respect to dx, but the variable inside tan inverse x function is x over a, right? So if we recall the formula or the technique we just used earlier, you see we just substituted u equals 1 over x, right? Because this is not the standard tan inverse x. So that means we have to do some adjustment here as well. So how can we do that? Well, so let's just assume that this value is equal to u, right? Like earlier. So if we have, say, 1 over a and d over dx of tan inverse u, you could write this as, okay, so du over dx equals 1 over 1 plus u squared, right? Sorry, this is going to be d tan of u, right? So we could just write so what we can do is basically, so you could write 1 over a, 1 over a, and then you could translate this part to the formula. Okay, this part to the formula, which is 1 over 1 plus u squared, right? But u is x over a. So we need to find the derivative of that, x over a, the derivative. Cool. So it is going to be 1 over a and 1 over 1 plus x squared over a squared, because I'm putting the value of u back. U equals x over a. Okay, so I'm putting the value back. And what is the derivative of x over a? So derivative of x over a is going to be 1 over a, because a is a constant, and d over dx of x, right? So that is going to be 1 over a. Cool. So that is something interesting. So you could replace this part as 1 over a, right? So basically we have another 1 over a over here. So let's continue. Let's finish this up. So because I have 1 over a and 1 over a, so I could just multiply them and get 1 over a squared, right? And then for the middle part, what I can do is 1 over a squared plus x squared over a squared. Cool. So this is going to be 1 over a squared times a squared over a squared plus x squared. So now I can cancel these two and get the answer 1 over x squared plus a squared. So this is the answer for this problem. Y equals 1 over a, arctangent of x over a. Okay, any questions so far? Yes, no? All right, so let's go to another problem, which is a continuation of the last session's problem, kind of, but this time we have arctangent with exponent function, correct? So that means we need to use the property of exponential derivative to solve this problem. Well, as usual, let's rewrite the problem again as y equals tan inverse of e to the power x. And the unique thing about this problem is it also gives us a value for x equals 0, right? So we need to do something after we get the usual answer like this. So this is actually a very common answer, but then they give us some initial or boundary conditions, so we have to take care of that too. So I'm going to show you how to do that. Okay, so the problem is y equals tan inverse of exponent or radical e to the power x, right? So how do you do this? What is the first step we have to do here? How do we proceed to solve this problem? Okay, so let's start with what we know and let's try to see if that fits into this problem. Okay, so recall, so derivative of tan inverse x is 1 over 1 plus x squared, right? So you could verify that with the formula sheet here in the front. So derivative of arctangent x is 1 over 1 plus x squared right here. So let's use that property. And also we have e to the power x. So what is the derivative of that? Derivative of e to the power x equals what? Well, so that is also e to the power x, right? So these are the two relations we're going to use, the formulas we're going to use, and a couple of other uh, rules like chain rules. Okay, so let's begin. As usual, let's write dy over dx. Okay, so dy over dx is d over dx of tan inverse of e to the power x, right? And like we just did earlier, we have to use chain rule. So how do we use the chain rule? So d over d tangent inverse of so I'm gonna write e to the power x over 2 for this. Okay, so how do I get e to the power x over 2 here? Well, let me finish this and then I'll explain. So d over e to the power x over 2, right? Then you multiply whatever you added to the, or like whatever you created in the denominator, which is x over 2 over d x over 2, and one more time dx over 2 of dx. You see, I just created few things here. So I created these two, right? They could essentially get cancelled. And also these two I created. And eventually what we will have is what we started with. Okay, one more time. So I created this portion and this portion so we could get cancelled and have something as the question. Also this and this. So why do we do this? Well, this is the chain rule. Okay. So we have to respect what we're differentiating with. So every time you see the variable of a function, so we have to create that in the denominators so that we can differentiate that. Otherwise it is not possible. So if you just write so let's say d of some function, let's say tan inverse of let's say e to the power x over 2 over dx. Yeah, you could directly get an answer for this, but inside the head somebody is doing like mental math to get the answer. So if you can do that, that's great, but if you don't, there's always a slower step, but definitely easier way to get the answer. So this step is really useful for me at least, and if you understand what I'm doing here in this portion, this is going to help you to solve any type of chain rules. So if you have any question, please ask me. I can explain it one more time. So we broke the problem into fractions, different sections. So let's do one by one. So this is somehow similar because we've been dealing with this type of problem over here. And also this is somehow similar to this, right? And this is very casual derivative. So that means let's solve it. Let's start with the easiest one. So this is going to be 1 over 2 times 1, right? Because 1 over 2 is the constant. And derivative of x with respect to x is 1, which is 1 over 2. So this is going to be 1 over 2. And so this portion is also straightforward if we have this recipe. So derivative of e to the power x with respect to x is e to the power x, right? So here you could substitute x over 2 with u. So you could call it as u. So essentially what you will have is d of e to the power u over du is going to be e to the power u, right? So that's how we can think of this problem. So that is going to be equal to e to the power x over 2. Okay, very interesting. So we have this answer and this answer. So let's do the first part. So what is the derivative of tan inverse some function with respect to that? So that is also straightforward. So we could use the formula here, this formula. So it will be 1 over 1 plus x squared, which is in this case e to the power x over 2 squared. Correct? Well, so that is going to be 1 over 1 plus e to the power x because we can cancel 2 and 2. Okay, very interesting. So now we are left with 1 over 1 plus e to the power x. Um, One last thing. Remember, we broke the problem into different sections so we could handle them separately, right? So now it's time to put them all together and get the final answer. Okay, the final answer is the first portion, which is 1 over 1 plus e to the power x, right? The second portion is e to the power x over 2. The third is 1 over 2, and they're all multiplied. So you could write this as 1 over 2 e to the power x over 2 and 2 times 1 over e to the power x in the denominator. So you could erase 1 and just write e to the power x over 2 over 2 times 1 plus e to the power x. So this is the answer for derivative, but we're not done yet, right? We have one last thing to do. So this is going to be, so given that the x equals 0, so if we have x equals 0, what happens to the derivative? Well, so this portion is e to the power 0, which is essentially 1, and this is 1, right? So that will be 1 over 2 times 2. So 1 over 2 times 1 plus 1, which is 1 over 4. So this is the final answer.